Section 5.2, binomial probability distributions. So in this section, we're going to talk about one specific discrete probability distribution, which is the binomial probability distribution. And it results from a procedure that meets these four requirements. There's a fixed number of trials. A trial is a single observation. The trials must be independent, which means the outcome of any individual trial doesn't affect the probabilities in the other trials. Each trial has exactly two outcomes, which we classify as success and failure, and the probability of success remains the same in all the trials. And here's some of the terminology or notation that we use. The probability, if we let S be success and F be failure, the probability of success is P, lowercase p, probability of success. The probability of failure is 1 minus P. There's only two outcomes, so P plus Q has to equal 1. N is the number of trials, which is fixed. X is a specific number of successes in N trials that we're interested in a particular problem. P is the probability of success in one of the trials. Q is the probability of failure. And then P parenthesis X is the probability of getting at least exactly X successes among the N trials. The word success is used here is really arbitrary, and it doesn't necessarily mean something good. It's just selected of the two categories. One will be called a success and the other will be called a failure. So let's work an example. When an adult is randomly selected with replacement, there's a 0.85 probability this person knows what Twitter is, based on results from a Pew Research Center study. Suppose we want to find a probability that exactly 3 of 5 randomly selected subjects know what Twitter is. Does this procedure result in a binomial distribution? And if it does, then identify N, X, P, and Q. So let's look at the four requirements. The procedure does satisfy the requirements. The first one is a fixed number of trials, which was 5. The 5 trials are independent because we randomly selected the subjects in the survey, and the probability of any adult knowing Twitter is not likely to be affected by the results from any of the other adults. Each of the trials has two outcomes. Either the person knows what Twitter is or the person does not. And for each randomly selected subject, there's a 0.85 probability this person knows what Twitter is, and the probability remains the same for each of the 5 selected people. Having concluded that, let's identify N, X, P, and Q. So N is the number of trials, which is 5. We want to know the probability of getting exactly 3 among the 5, so X is equal to 3. P is the probability of success, which we called getting a person who knows what Twitter is, and for this study it's 0.85. And the probability of failure is 1 minus P, or 0.15. Again, it's very important to be sure that X and P refer to the same concept of success. In this example, we used X to denote the number of people who know what Twitter is, so P must be the probability that the selected person knows what Twitter is. When sampling without replacement and the sample size is no more than 5% of the size of the population, we'll treat the selections as being independent even though they're actually dependent. And here's what the formula looks like for the binomial probability. If you're going to do it by hand, which we're not going to do, we're going to use technology, but I just want to give you a little motivation for what it means. So the probability is given by, and we have N, where N is the number of trials, X is the number of successes we're interested among the N trials, P is the probability of success, and Q is the probability of failure in any one trial. And so just a little bit of motivation here. The first part of the formula right here is the number of outcomes with exactly X successes among the N trials. So if we have 5 trials and we want 3 successes, we could get the first 3 people being a success and the last 2 being failures, the middle 3, and so forth. So there's a lot of different ways that can occur. And then here's how the probabilities work out. So we have 3 successes in our example. So it would be the probability of success raised to the 3rd power. And then the rest of the people in the sample were failures. So their probability would be Q times that many people or subjects in the study. So again, let's go back to the Twitter example. There's a 0.85 probability that a randomly selected adult knows what Twitter is. And we want to find the probability that among 5 adults randomly selected, exactly 3 know what Twitter is. Okay, so here's how we do it by hand. We take that formula, and again, we're not going to use the formula. We're going to use StatCrunch, but again, you would use your calculator. do the calculations here, and it comes out to be 0.138. So the probability of getting 3 people among 5 who know what Twitter is, given the probability of one person knowing is 0.85, is 0.138. Okay, so now if we're going to use technology, much easier. In StatCrunch, you use the command stat calculator binomial, and down here you enter in n, the number of trials, the probability of success, and then this little window here, X, and you have a drop-down menu for different combinations. You could have greater than, less than, greater than or equal to. We just want X equal to 3. And then when you hit compute, the probability is going to come out in this little window here. And there's my probability, 0.138, which is the same probability that we got if we used the formula and did it by hand, but it's much easier and less cumbersome to use StatCrunch. Another example, overtime rule in football. We previously noted between 1974 and 2011, there were 460 NFL games decided in overtime, and 252 were won by the team who won the overtime toss. Is the result of 252 wins in 460 games equivalent to random chance, or is it significantly high? We can answer that question by finding the probability of 252 wins or more in 460 games, assuming that wins and losses are equally likely. So we're going to use n equal to 460, and we're going to say it's a 50-50 chance. So we're going to, the probability of success be 0.5, and then we want to take the probabilities for every value of x from 252 through 460. Now, this would not be practical to do by hand, so we did it in StatCrunch. So again, in StatCrunch, I did stat calculator binomial. I entered in the n, 460, the p, 0.5, and then I changed my drop down here to greater than or equal to 252. And here's my probability, 0.0224, which is pretty low, less than 0.05. So it shows that it's unlikely that we would get 252 or more wins by chance. So if we rule out chance, we're left with a reasonable explanation that the team winning the overtime toss has a better chance of winning the game. Another example, in a Harris poll, 60% of adults believe in the devil. Assuming we randomly select 5 adults, use StatCrunch to find the following: the probability that exactly 3 of the 5 believe in the devil, the probability that the number of adults who believe in the devil is at least 2, and the probability that no more than 1 believes in the devil. So I gave you some different wordings here so we can see how you adjust that drop-down menu in the binomial tool. So for the first example, we've got 5 trials, and we've got a probability of success of 0.6, and I'm going to use an equal to for 3. So pretty straightforward on this one, and we get a probability of 0.3456 or 0.346. Now we want to do the phrase at least 2 successes means the number of successes is 2, 3, 4, or 5. So my drop down I'm going to do as greater than or equal to 2. So right here I select greater than or equal to 2. I put my same n in and my same probability, and I get 0.913 approximately. And then last one was at most no more than 1 success. So that means 0 or 1 successes. So again, this time I'm going to do a less than or equal to right over here, and I get a probability of 0.087. And we can use the binomial distribution. We can find the mean and the variance and the standard deviation, and these are quite easy to do. These we will do by hand. So the mean of a binomial is simply the number of trials times the probability of success. The variance is NPQ, and then the standard deviation is simply the square root of the variance. And going back to our range rule of thumb, significantly low values are going to be 2 standard deviations below the mean. Significantly high are 2 standard deviations or more above the mean. And let's go back to the football example, and let's compare what we get here with significantly high to see if it matches up with what we got when we did the probability. So we want to find the mean and standard deviation for the number of wins in a group of 460 games if we use a probability of success of 0.5. And then we want to find use the range rule of thumb to find the values that separate the number of wins that are significantly low or significantly high. And then finally, is the result of 252 overtime wins in 460 games significantly high? Okay, so the mean and standard deviation, again, pretty straightforward. NP, 460 times 0.5, so I would expect to get 230 games. And then NPQ, under the square root sign, I take 460 times 0.5 times 0.5, and then take the square root, and I get 10.7 games. So for a random group of 460 overtime games, the mean is 230 wins, we're talking about here, and the standard deviation is 10.7. And let's do our significantly high and significantly low. So if I take my mean and subtract 2 standard deviations, I get 208.6. If I take my mean and I add 2 standard deviations, I get 251.4. And remember, we had 252 wins. So therefore, our result was significant, and this agrees with what we found when we used the binomial calculator in StatCrunch. So it would be significantly high. So significantly high number of successes if the probability we calculate is less than or equal to 0.05, and significantly low if the probability we calculate is less than or equal to 0.05. And there is a StatCrunch video for this section. Here's a link here, and there's also a link in the unit module in my courses.